Okay, so if I draw a layout, this can be a problem on the final exam. Okay, if I draw a layout like this, that's how I'll let you guys to do it now. Okay, and then that's metal 2. That's a contact. So this is metal 1, metal 2. Right? And then I draw a dashed line across this layer. And I'm asking you to draw a cross-sectional view of this line. So this is the top view of the layout, right? So I'm going to cut it. So it's a wafer underneath it. And then what does that look like on the cross-sectional view? Take 1 minute to draw it ourselves right now. Okay, now let's take a look at it. So the first one should be the filled oxide. This can be confusing. I still don't know what we can do with it in the future. Okay, so if you look at this figure, it's not directly a layer on the top of the silicon wafer. It's getting into it a little bit, and then on the top as well. So because it diffuses into the wafer, so that's why it is able to reduce the crosstalk between the diffusion nodes here. So it helps. But whenever we don't have any NMOS, N plus and P plus over here. So actually these filled oxide connect to each other to all this. So it's like a flat layer here. It's not being opened up. So that's why, since I don't have, it's a 2 metal layers, I don't have any N plus and P plus, right? So that's why I can draw a layer of flux, filled oxide. On the top. So what's next? Poly 1, poly 2. So C5 has 2 poly layers, just keep in mind. I mean, sometimes you are asking like, why do we need a poly 2? Poly 1 is used for gates. So why do we need a poly 2? So I'm going to cover that pretty soon. But you do need that insulation layer here to host that these 2 poly layers. Do you have anything to be drawn in insulator 1 in this layout? No. What about here? You got metal 1, right? And what does that look like? What that looks like based on this sampled area from the cross-sectional view. yeah, like a line, right? You have to draw it in scale because it stops here, cannot draw it here. So it has to be the same length. So that's metal 1. I don't have much space over here because it's too close to this one. But you can draw to make it a little thicker. And then what's next? There's metal 2. So these are the insulator layers, right? I got a COVID vaccine booster on Saturday. It really got me. I got a fever and pain on my body, my muscle for the whole weekend. It happened for the first time in March when I got the first shot. Now I got a booster, it's still the same effect. Yes. All right, that's metal 1, has to be the same length, and be careful. So that's a via. When you are drawing the via, it has to be the same width as well, right? So the via, it should contact both the metal layers. It drills a hole to the upper layer, and then metal 2 has to be exactly this wide. And it must make the contact with the via. All right, any questions on this? So look at your drawing and see if you have the same length, same width for everything, and also see if you have the contact between the via and the 2 metal layers. So the metal layers are, so that metal layer, for example, metal 1 sits at the bottom of this insulator layer. Same for metal 2. So that's why when you draw it, for example, that's the insulator layer, you don't want to draw the metal 2 here, okay? It's at the bottom. That's how you draw it for the cross-sectional view. Make sense? It's pretty simple, but you don't want to lose any points on this. So you probably have seen there are multiple vias, multiple holes on the layout for intersection between the 2 metal layers. So for example, here's metal 2, and that's metal 1. So at the very beginning, if you do not have really big wire, then there's only one via. And if you make it wider, sometimes you should need it to be wider. I don't know if you have noticed that. Will that be only via here or multiple vias? Have you seen that? No? So if it's getting bigger, so there are multiple vias instead of one. And why is that? It just need to make the contact, right? And if you drill one hole there, it's going to make the contact. If you drill multiple ones, it's going to make the contact as well. So why it bothers itself to have multiple vias instead of one? So this is written the rules. And whenever we are laying out a circuit in electric VLSI, we picked up the 300 nanometer. It's called CMOS. It's called Lambda Rules. It's a very simple rule compared to the TSMC's layout rules. So the rules defines the distance between the metal parts and just pretty much everything, the distance between the metal, between the poly, the width, the minimum width of the metal, minimum width length of the poly, things like that. So that's the design rules or standards for the layout, and you couldn't see it. The thing is, it's being controlled by the software, and the ones we are using is called Lambda Rules. So it's using a unit. For example, 300 nanometer is 1. So the distance between the two vias has to be minimum 2, right? So it's going to be 600 nanometers between the two vias. And also the rules defines, in an area like this, how many vias are required by that unit area. And why is that? Why the rules should add more vias whenever the intersection becomes bigger. So something like you got a wire and resistor, and there are 6 resistors because the via, for example, is the metal. I can consider that one as a small resistor. So there are 6 resistors, and that's metal 2, that's metal 1. It's making contact between these two. Huh? More vias actually getting you less resistance. These are in parallel. So parallel resistors are reducing the resistance, right? So this is the first point, is to reduce the resistance. What's the second point over here? So it is able to improve the yield. Remember, we talked about yield. If you only have one via here, if that one fails, it's disconnected, these two metal layers, right? You got 6, you'll have some redundant vias, can be a backup plan over there. But why not getting more vias over here? Yes, it's right in the minimum space, minimum length and width. Only one can fit in there. Okay. Active and poly layers. So what the active layer does is it opens flux. If you remember that, if there's a flux, nothing can penetrate the flux and arrives the silicon substrate. So it cannot dope any N plus or P plus, any MOSFETs to the substrate. So you need a layer. So the layer is just a layer on the mask. Remember the mask. So it is able to open up the flux. So for example, here's the silicon wafer, and flux is over here. That's flux. The reason I have to draw it a little bit into the substrate is because of this, right? It's getting into it. It opens up here, so I got an opening, and it is able to dope this P plus material into the wafer. Okay, but you have to open it up first. All right. Then, for example, this is unselect. This is the active layer. All right. So it opens a window on the top, and it is able to allow the material to reach that substrate and getting that doped. And you haven't noticed that, you know, on the electric VLSI layout view. I don't know why it doesn't work. Okay. So there are two layers on the N+. So just take a look at it when you are doing the lab on Tuesday. It has the active layer, which is exactly the area will be doped with a N+ or P+. And there's another layer called unselect or P-select, which is a little bit bigger than the active layer. So that's the active layer. That's unselect. And the reason they want to do that is because if you have done any photolithography with different layers, you'll know that it's super difficult to align this one directly on the top of this opening. You know what I mean? So this has been opened up, and now you are trying to dope this area with either N+ or P+. You want to make that, for example, here's a window. You can throw all these materials through that window to it. And if you just make it exactly the size of the active layer, then it can be misaligned. Then this part probably cannot get doped. So I have to make it bigger, so it has that tolerance. You know, whenever there's a misalignment, you can still dope everything into here. So actually there will be some material reach the FOX, but doesn't matter. You know, FOX is just oxide. It's gonna stay there. Whenever you need to etch that FOX layer away, it's gonna do that. Or there might be some developer can remove that dopant on the top, or it doesn't have to be removed at all. Doesn't matter. So the FOX is just a FOX oxide layer. It's not going to affect the functionality of the MOSFETs. So that's why it requires that unselect layer, which is a little bit bigger than the active layer. And if I draw it, okay. So before I draw the FOX, and for example, this is unselect, so I'm gonna dope N+ to the substrate, right? So let me know where should I draw the FOX? From here or from here? Here? Okay. So here will be the diffusion. And what's that going to be? N+, right? There will be a little N+ here, which is fine. All right. Okay, one more thing. I think I haven't mentioned that in the past. So for the NMOS, for the PMOS, I'm sorry, PMOS, P+. So why the PMOS has to be fabricated in N well? So the substrate is a P-sub, is a P-type. Usually it's a P-type substrate. So it's rather a silicon wafer doped with P material, not that concentrated as a P+, but they are P little plus, right? So if you have that P material here, which has a lot of free holes, and the P-sub also has free holes, they are actually shorted together. So the diffusion nodes here are not going to function at all because P plus, if you have a P plus in a P sub, they are shorted. Not going to work. You have to have an N well to host the P plus into the N well. Okay. And so let's see, if we make the N well a little bit bigger, and I usually need an N plus. Remember when you have a PMOS on the top, we'll do the layout. Remember, we'll do the layout. And we have a top rail on the top to connect it to the VDD for the PMOS. So on the layout, what that looks like for the cross-sectional view. So what is that top rail really is? What is that? Do you still remember the name of it in electrical VLSI? I kind of forgot it. What's the name of it? It's not working. It's not a well, right? Yeah. So take a look at it tomorrow when we're doing the lab. No. Oh, an act? Did you say an act? Probably. And where is the an act over here? That little thing. And does that make sense after we talk about this thing? So an act is gonna dope n plus the substrate, right? Okay, so the n act is gonna make this thing here. And why is the VDD? It's just the n plus. Why is VDD? Why is becomes a top rail? The reason this is VDD is because on the top of this node, whenever you want to connect this one to something, it has a metal contact on the top, right? Which is the via. So the via is a hole. The drills a hole and then fill it up with metal material, right? So that's a metal, and the reason we can name it as VDD is because we just name it as VDD. We did a Control I, name it as VDD. That's why it's VDD, which is, if you do not connect that pin to VDD on the chip, it's going to be nothing, just a floating wire. It's nothing. We just want to connect that one to VDD, right? So here's the question: why should we connect that one to VDD? So here's a PMOS, right? So P plus over here, the P plus, and that one. It's a pretty long rail actually. So on the wafer, it's actually a lot of. It's a. How do I want to draw it? So for this one, it's gonna be this, right? A pretty long N plus. So what are these vias? It's one piece. It's not separate ones. I just labeling that. So what about these ones? They're just different vias. So you have a long wire has multiple vias on the top, right? And then you made a connection from P plus to the N act. And then you short this to VDD. So it's on the chip, or in the simulation, you just connect a VDD signal to it, 5 DC voltage to it. And so you can provide a signal to the PMOS. So here is a question: why we have to connect this N act to VDD? It's a different NACT. So this N plus, just forgot the name, just pay attention to it on Tuesday. So this N plus is in N well. So it has a different name. So this N plus is different. It's not N well. It's directly in P sub. So they are different. Okay. So the NMOS, if you look at the shape, from the layout view, you can notice that PMOS and NMOS, they have different colors, and some of them are slashes, some of them are dots, right? I remember the yellow slashes, it's a P sub, and dots, the black dots, is either N plus or P plus, I forgot, but you can pay attention to it on Tuesday and take a look at it. And also, you look at the diffusion, so you can grab a NMOS, right? Remember, that's a little NMOS. Does it have a contact? It doesn't. You connect ourselves, right? So grab one here, you make the connection, grab another one here, make the connection, and then you move them together in the same direction. So, but if you look at this one, look at the dots, the patterns here, and compare to the N here you used for this top rail, they should be different. Because one is should be fabricated in the N well, another one is directly in the P sub. So now let's look at this one. So if these N pluses are in N well, then it's actually shorting the N plus to the N well. Is that useful or is it a disaster? This is what we are doing here. This is actually what happens to it. So for the NMOS, that's PMOS, right? Remember for the NMOS, we have a P plus, and that's a P sub. And we have to short this to the ground. That's how we can short P sub to the ground. Okay, and if this NMOS, the source of the NMOS need to be shorted to the ground, then we just do this. We want to keep the P sub at the lowest potential of the circuit because we want to get rid of what? Body effect. What's the consequence of body effect? It increases the threshold voltage, which makes it harder to turn it on. Why it's going to increase the threshold voltage if there's a body effect? So if you do not short P sub to the lowest potential, then this is a diode, right? So if at some point P sub has a little bit higher potential than the N plus, it's going to dump current to the channel. Since it's been working super hard to inverse the channel with electrons, now it's dumping current to it, which will neutralize the electrons. So it's making it even harder to inverse it. So that's why you need a more voltage to turn on the gate. But now, since P plus is directly shorted to P sub, and there's no way you got a wafer, right? How can you connect the P sub to the ground? I mean, you are just looking at the back of the wafer. You flip the wafer on the back. You solder a wire to it and connect to the ground. No, it's not working that way. So the wafer cannot be soldered to the metal. You know that, right? You have soldered anything. Probably you guys haven't, but you have in some of my labs. So the solder material only attached to metal when it's hot. So that's why you have very little tiny of pads, the metal pads on the PCB board, and the pads are very close to each other, and you just dump solder material to the board, to the pad, and just stay on the pad instead of shorting all the neighboring pads. Why? Because the solder material, whenever the solder is being melted, it only stays on the hot metal, not the fabric material, the PCB. Okay? So not mention the wafer, it's a silicon. You can never solder something on silicon, right? So this, you flip it and solder, whenever, if you look at this, the drawings on the textbooks, they will just show you that, hey, the P sub is grounded. They'll just show you this is grounded like that, drawing a ground at the bottom of the P sub. But actually, it's not working in that way. You can never short the wafer to the ground by shorting the bottom of the wafer to the ground. You have to get a P plus over there. You have to dope it with a P plus, and you know that the P plus is the same material as the P sub, very similar material, so they are shorted together. And then you connect this P plus to the ground. How? Yeah, metal 1, and then metal 2, and then metal 3. And then on the top of the wafer, so after all these metal layers, so let me know when I should stop, okay? Do I need more? Huh? Really? Let's see. Fox, poly, metal 1, metal 2, metal 3. So there's a top layer is another, it's called passivation layer. It's also a silicon dioxide, but it is able to open up a window. So this is metal 3, right? This is metal 3. Fox, poly, metal 1, metal 2, metal 3. So this is metal 3. And it is able to, hey, so actually, let me see. Depends on different process. I don't know if there's another passivation layer on the top, but can stop here, which is fine. So just open a window here on the top and make the contact, use a bonding wire to bond it to the pad. There's a pad on the IC package. Okay, so here's the IC. And with all the pins. And internally, that pad is shorted to that pin so you can ground it. Then the chip is grounded. Okay, so here's the P plus. P plus for the P sub. And just drill the holes, make the vias. So that's how you ground the P plus. And you do need that P plus over here because you want to short it to the P sub. And that's how you can ground the P sub to avoid body effect. So now let's look at this one, this NMOS, this PMOS. So this is NMOS, right? NMOS. For the NMOS, you need a P plus. For the PMOS, you need N plus. Now N plus has to be in the N well. So what's the name of this guy? It's called a well contact. For this N plus. For this P plus, it's called substrate contact. It makes sense over here, right? So it's making a contact with the well. So in some of the technologies, we call, because this is N well, right? So that's why they call this P sub is a P well, but actually it's not a well. It's just directly the P sub. You don't have a P well here. It's directly just a P sub. So this is the N well, and we want to do the same thing here because this N plus is going to short it to the N well. And whenever we are connecting this to where? To the highest potential in the circuit for the PMOS, it's reducing the body effect. How? Yeah, so it's connecting. So if I connect N plus, this N plus contact to 5 volts, this is what you have, I should have been doing here, right? 5 volts. Yeah, been connecting the top rail to 5 volts. And whenever you are doing that, it's shorting the N well to 5 volts. Here we are shorting the P sub to ground. Here we are shorting N well to the highest potential in the circuit. So if you do not do that, for example, if you do not short N well to the highest potential, then P plus and N, it forms a diode. Okay, so what's going to happen to it? So for the PMOS, it attracts what to form the channel? Holes. It's been trying very hard to attract the holes to here. So the diode here, if the diode conducts current, what's going to happen? Current flows in that way. So the direction of the current is the same direction as the flow of the positive charges, right? So holes are positive charges. So the hose is going to flow to N well. So you are wasting your holes. So it's going to take more efforts for the gate voltage to attract more holes. It's also increasing the threshold voltage. By connecting the N well to the highest potential in the circuit, in the entire circuit, whatever you have on the circuit, you have to connect all the N wells to the highest potential. Then at the cathode, because N well is a cathode of the diode, so if you have the cathode of the diode to be the highest potential, it's never able to conduct current because the cathode is the highest potential, right? You even need like 0.7 volts to turn on the diode. There's no chance the diode will be turned on. The same for this one. The diode can never turn on. So if I have some of the op-amps you have been using in the lab, it's being powered up by plus and minus 15 volts. So in that kind of circuit, do you have a ground over there? No, ground is over 0. Keep in mind, ground is over 0 volts. Whenever I'm talking about ground, it's 0 volts, period. Huh? Where's the ground? It's somewhere else, right? So you didn't ground anything in here, but because the reason that this one is negative 15 volts is because there's a 0 volt somewhere else. So it's compared to 0, it's negative 15. There must be a 0, right? So it's just a reference voltage. Remember how can you make that happen? How can you make a negative 15? Plus minus 15 volts? So I have two 15 volts batteries. How can I make it happen? How can I make a plus minus 15? No. So what's the key point to make it plus minus 15? Just 2 words. 3 words. Ground the center. 0 volts, like I said, forever. Ground is 0 volts forever, permanently, period, okay? So 0 volts is, because the battery is 15 volts, is from the manufacturer, I know it's gonna drop this point, 15 volts to this point, right? So it's gonna drop the voltage by 15 volts from here to here. So here will be negative 15, here will be 15. That's how you can supply that plus minus 15 volts to the op-amp. And here's the question, do you have a ground in the circuit? Yes. So still need a ground, right? So for this op-amp is amplifying a signal, but it must have all the other circuits, you still need to have a common ground to ground everything to here instead of here. Okay? So for example, that op-amp is made of CMOS transistors. So you have top and bottom rails. Should you connect the bottom rail to here or here? Since you have a choice right now, right? Yeah. Okay, it has to be the lowest potential in the circuit to get rid of the body effect. Doesn't matter how low it is, just need to be low. Sounds like a comment for the president election debate. When they go low, we go high. Doesn't matter how low it is. Still have 10 minutes. See more examples for you guys. So here's a summary for the select and active area. So the select area can be unselect, can be p-select. Is it larger or smaller than the active area? So what the active layer does, remember, opens the window. On Fox. So here's active. Opens the window on Fox. You're imagining, like wondering how that works. How it is able to open the window on Fox? Huh? Yeah, etch it. So use a photoresist, a different process, right? So you can definitely do it, you know. So this area probably, so all the other areas probably were protected, right? But only this area was not. And then you immerse the wafer into a developer or etchant that's going to etch this area. So that's how you can open the window. And so what is unselect? Unselect is a bigger area compared to the active area, because we want to make sure that we can dope the entire opening with that dopant. So we want to make it a little bit bigger. You know, what's the reason that it's super hard to align this window to here? It's very small. Like nanometer technology, how can you do it? I mean, even you are using like micro manipulators, it's still very difficult. Just want to make it bigger. For poly layers, there's another oxide layer in between the poly and the wafer. That's poly 1. So Fox, this time I drew it inside, but you know that it's actually not really, right? You know what that looks like. Okay, and did you see the oxide layer in between the gate and the wafer? So remember the name of MOSFET? What does MOSFET mean? MOSFET. So what is FET? Field effect transistor, right? So what does that mean? It's comparing to BJTs. So BJT doesn't have the field effect. It directly dump current into the junctions. This is the field effect. Why? Because there's an insulator in between the gate and the transistor. It's not directly dumping current into it, so that's why it's less power consuming. That's why it's a better technology to be used. In all the low power designs, you don't want to use a lot of BJTs, you want to use MOSFETs. And so what's the field effect? It's an electric field, right? It's the voltage applied to here, to the gate, and then it forms the electric field instead of directly dumping current into it. So electric field, for example, for the PMOS, it attracts holes. For NMOS, it attracts electrons. So that's a field effect, right? So that's why it's not making a direct contact. So it has a very thin layer here. It's called gate oxide. Gate oxide, which is here, the gate oxide. It's not a Fox. It's not a field oxide. It's a gate oxide. And it's thinner than Fox. Okay, just let you know that. And then the poly layers can be used as resistors. So what's the material we used as resistors in the layout? NWL. So we have used NWL. Polysilicon, the gate material, can be used as a resistor as well. So you know that it has a lot of resistance. You don't want to directly, if you have a long distance, you don't want to use poly to make the connection. You want to drill a hole with a via to use metal 1 as a trace, right? So here's a table for the resistance to compare poly and metal. Is 200 ohms per square. It's a lot. For metal is 0.1 ohms per square. Well, it's 200 ohms, my goodness. So I probably have to redesign some of the layouts in my tutorials. There were some pretty long ones with a lot of squares in there. So they're introducing like 2 kilo ohms. Very possibly, right? Okay, if you want to reduce the resistance of silicide, the resistance of the poly, you want to deposit a layer called silicide on the top. So for example, here's a polysilicon, and that's some top layer. Just the material is more conductive. It's usually made a mixture of metal and tungsten. I don't know what the metal is, but mixture, like usually aluminum or copper. Aluminum or copper with tungsten. And this is called silicide. To reduce the resistance of the power layer. Poly wires. All right. So we'll continue working on the C5 layers, and then we'll start working on the model for digital design on Wednesday. Okay? See you on Wednesday.